Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. First of all, thank you for watching our video. We are from team PBL-TRPL406. In this video, we will present our project entitled Sigma, Smart Integrated Guardian for Monitoring and Assistance. And let me introduce our team. First, Jatuh, our team leader and AI machine learning engineer. Muhammad Hasan Firdaus, as system architect and IoT hardware engineer. Hasna Fadila Ramadan as a software developer and cloud engineer, Nanda Prasatyani as a IoT hardware engineer, Ivan Awarin as a business analyst, and Muhammad Maulana Yusuf as a UI/UX and product design engineer.
Let's begin with the problem. For blind and elderly individuals, walking independently is not always safe. Every day, obstacles can lead to falls or accidents, and without a monitoring system, their family might not know something is wrong right away. So, to solve this problem, Sigma is designed to help users stay safe and independent through real-time locations monitoring and emergency alerts. Now, let's take a look at how Sigma achieved this through its main features. To achieve this goal, Sigma is designed with three main features. The first is fall detections. These features detects when the user falls and automatically sends an emergency alert to their family, so help can arrive as quickly as possible. The second is obstacle avoidance. The smart can use sensor to detect nearby objects and provide vibrations or sounds warning, helping users move more safely. And the third is emergency tracking. These features allow the user's locations to be monitored in real time by mobile applications so family members always know where they are, especially during emergency. With these three features working together, Sigma help users move more safely and independently while giving their family peace of mind, knowing they can respond quickly whenever help is needed.
Okay, next, we have a three flowchart. First is fall detection flowchart. These flowcharts show how the system detects a fall. So the process starts when the sensor keeps checking the user movement. When a fall is detected, the system checks if the user does not move for 1 minute. If the user moves again, the system goes back to monitoring. However, if there's no movement, the system sends a notification step by step. The first notification, the second notification, and finally a notification to nearby user if there's still no response. After someone responds or the user moves again, the incident is marked as finished and the system continues monitoring until the device is turned off. And the second is obstacle detection flowchart. So this flowchart shows how the obstacle detection feature works. The process starts when the distance sensor keeps reading data to detect object in front of the user. If no object is detected, the system continues monitoring. If an object is detected, the system checks whether the distance is with the safe limit. If the object is too close, the device gives a warning by vibration or buzzer. After that, the system continues monitoring again until the device is turned off. And last is GPS location flowchart. So these flowcharts show how the system sends the user location. The process starts by turning on the GPS module and then the system with the GPS coordinate. If the location is available, the system sends it to MQTT. If the location is not available, the system uses the last known location. After that, the system waits for a certain time and sends the location again at a regular interval until the device is turned off.
Alright, now I'm going to explain the hardware architecture of our Sigma Smart K. So the ESP32 here is the main controller connected to the GPS MPU6050 ultrasonic sensor, SIM800L, panic button, vibration mirror, and buzzer. The system is powered by two lithium-ion batteries connected with a BMS and regulated using a step-up and step-down to provide a stable voltage. The next slide is the hardware integration inside the 3D printed enclosure. So the ESP32, the GPS, MPU6050, SIM800L, and ultrasonic sensor are soldered directly onto the custom PCB. And the remaining components are connected through terminal blocks using wires, making the system easier to assemble and maintain while keeping the design compact.
All right, now we are going to talk about the device specification and operation of Sigma. At the center of our system is the ESP32 microcontroller, which connect all the sensor and handle the main data processing. For fall detection, we use MPU6050 sensor combined with a tiny ML model to detect abnormal movement. if a fault occurs and no movement is detected afterward. The system will trigger an emergency alert to the mobile application. User can also manually set an emergency signal by pressing the panic button. For location tracking, as GPU Neo M6N module provide real-time coordinate. Meanwhile, the ultrasonic sensor that detect nearby obstacle and active buzzer and vibrator motor to give the user warning. All of this data include fall event, SOS signal, and location update is sent by the SIM800 V2 GSM module to the internet using the MQTT protocol. On the server side, the backend process and store the data in a PostgreSQL database. Then send notification to the mobile app using Firebase Cloud Message FCM. This allows caregivers to monitoring the user condition and location in real time, ensuring a fast response during any emergency.
Okay, thanks Zico. Now I'm going to show our implementation and the results. In our project this semester, we have an ecosystem consisting of 3 main software components. For the embedded device implementation, our team successfully designed a custom PCB and a 3D printed case. In terms of functionality, all of our modules are successfully connected to the ESP32 and are sending data to the server. We implemented the embedded software using C++ with Platform.io. Next, we also implemented a web-based admin application. This application is specifically designed for administrators to manage the list of devices in our system. Information such as device ID and secret key, which will be stored on the embedded device, is registered through this application. The last component we implemented is a mobile application for device guardians and volunteers. We implemented the login and registration functionality. Guardians can pair their device using a pairing code or by scanning a QR code. They can also change device configurations, such as enabling or disabling nearby device notification. For our core features, on the home screen, Guardians can view the location of their paired device. Volunteers can see the location of nearby devices that need assistance. Notifications are also delivered through the other system using Firebase Cloud Messaging. There is also an incident screen that displays active incident and the incident history, such as fault detection or SOS alert from pirate device or nearby device. Finally, Guardians can view the movement history of their device. As of July 22, we have successfully implemented all of our planned functionalities except for detection, because the device case has not been completed yet. We are currently finishing the case, and after that, we will implement the fault detection functionality.
Next, I'd like to share some lessons we learned during the development of Sigma. First, in hardware and IoT, we learned that a stable power supply is very important to ensure the device works reliably. We also found that good soldering quality has a big impact on the overall performance and durability of the hardware. Second, in AI and machine learning, we realized that building an accurate fault detection system requires a suitable dataset. At this stage, we still need to collect more data and continue improving the machine learning model. In design and management, we learned that the caching should not only look good, but also be durable and practical to boot. We also had to balance functionality, cost, and component availability when selecting the hardware. Lastly, in teamwork, we learned the importance of continuous research, effective communications, good task allocations, and proper time management to keep the project moving forward. Overall, this project has given us valuable experience, not only in developing an IoT-based smart device, but also in collaborating as a team to solve real-world problems.
Here are some documentation photos for our project development process. This picture shows the hardware assembly, component testing, application development, and system integration. Through this activity, we were able to evaluate our progress, identify problems, and continuously improve our prototype. That's all for our presentation. We hope our project will be useful in the future. Thank you for watching. Wassalamualaikum warahmatullahi wabarakatuh.